I know, you guys are so smart.
Oh, stop it.
All right, let's talk about motors. Actually, I'm gonna talk about it first, and then we'll watch. Oh, sorry, everyone at home. Hope I'm not making you dizzy.
At least the camera's pointing the right place.
What's that?
I said at least the camera's pointing the right place.
At least
For once. Okay, so I got a magnetic field. This is kind of like number 17? Is that what it was? With the loop in the magnetic field. 11. It's like number 11. Only we're actually going to be able to use this to do something useful. So this is essentially going to be a basic electric motor. So I have a loop of wire, a square loop of wire. I have drawn the inputs and outputs for the current, but we're going to ignore the torque, the forces that are going to act on those wires. We're going to ignore them. We'll assume they're negligible. So we have a loop of wire in a uniform magnetic field. The plane of the loop is in the direction, the magnetic field lines are the same in the same plane as the plane of the loop, at least to start. The current's going to come in here, and then it's going to go across that guy, down this guy, that guy, that guy, that guy, and then out that way. This dimension for the loop has length A. This dimension has length B. And first, what I want to say is what parts of the loop are going to feel forces, and what parts of the loop are not going to feel forces. And so let's talk about first this part of the wire. Okay. No force, right? There's going to be no force there because I crossed with B. Can't do that. They're 180 degrees. I cross B is IB sine theta. Sine of 180 degrees is 0. So no force on that segment of the loop. Similarly, we know the current's going to be coming back in here, same direction. No force on that segment of the loop. What about this segment of the loop? No force. So we have the same current going through that segment of the loop, 0 force acting on that segment. Here, though, I do have an angle between the current, and remember, technically what it is, it's those little DL vectors, right? So I have an infinitesimally small current displacement on that wire, and according to the equation on your formula sheet, the magnetic force is the integral of I times dl cross B, which again, in this instance, simplifies to I times L times B, or if you like, Bill, right. dl cross B is dl B sine theta. So and I and B are constants, so you pull them out and you integrate dl. When you integrate dl, you just get the length of this guy. So actually, in this case, it's not going to be I. It's not going to be L. I'm sorry. Let me go through the whole scenario. I know dl cross B is B times dl times the sine of the angle between those. Sine of the angle between dl and the magnetic field is going to be 1 because the angle is 90 degrees. And so dl cross B will end up just being B times dl. And so the magnetic force is therefore the integral of IB times dl. I and B are constants, so I can pull them out, and I just integrate dl over dl. But dl is not just L. In this case, it's what? A. It's going to be A here, right, on this particular wire. So this is the leftmost wire. And so the magnetic force here is going to be I times B times A. Okay. And what direction does it point? Points up, right? I cross B. Well, I is kind of out, right? Kind of out, cross B. It's going to point up. So this segment of wire feels an overall force that points up. A magnetic force. What about this guy? The rightmost wire the current's going this way.
Exactly the same as down.
Exactly the same. Everything's the same, but down. So the rightmost wire.
That's because the sine of the angles, I think, were like plus 180, right? So it'd be. I don't know. It's the exact same.
I
It would be negative.
cross B. Right.
I'm saying, like, would the force be like a negative force? Like, would you come up with a negative answer?
You won't come up with a negative answer, but you just
Oh,
have to.
Never mind. Yeah, obviously, you don't. Yeah. I know.
I mean, technically, because the angle between these guys, the angle between these guys is going to be 180 degrees more than that.
Oh, yeah, so I was right.
So yeah, you're right.
Okay.
If you want to be all, logical about it.
I hate logic. Physics? No.
I said up. Same, but down. Right, so now I have a force here that's going to point down when I do my cross product.
Now we're seeing alternating currents.
Someone's thinking ahead. Stop it. Right. So, what I get then, if I fix this loop of wire and have a rotation axis running through it, I then get a torque, right? This guy creates this force creates a torque about this axis of rotation. This guy gets a force that creates a torque in the same rotational direction, right? Both of these forces want to cause clockwise rotation. And so I then get a net torque equal to 2 bil. Yes. 2 IVA.
Oh.
So it's going to be 2 times IBA. That's the force, though. That's just the force times the lever arm. What's the lever arm for both of those guys? B over 2.
Yeah, good stuff.
Little b over 2. So the 2's actually cancel. So the net torque is then going to be what? IBAB.
The first half is in caps and the second half isn't.
Wait, what?
The first half of the answer is in caps, and the second half isn't.
Yeah. Although in my notes I have it IAB, I little a little b, big B. But whatever, it doesn't matter. Multiplication is commutative, so it doesn't matter. Okay, so we good with that? You understand? And notice it's very similar to number 11 on the quest assignment. Right?
Right, all in base SI units. So it would actually be
It'd still be Newton meters.
cube per second. Newton meters squared per second squared.
It'd still be Newton meters.
Yeah, because it's torque, right?
So kilogram meters squared per second squared.
Yeah. Okay. And that's an exercise for you to do at home. Okay, so now Timothy alluded to a point, though. Very important point.
Oh my.
When this thing, let's say it's rotated 90 degrees. And so this wire is now at the very top. Right?
You get an electric toothbrush.
You're going to like
Like it rotates. It's gonna
any electric motor. Any
yeah, but
electric
it's
motor.
gonna rotate instead of going a complete circle infinitely. If it's direct current.
What happens on this wire here? Yeah, and we're talking direct current. Right? We're talking direct current. This we get an upward force. As the wire rotates, doesn't the force always point up?
Yeah.
Always, right? Doesn't this force always point down? So once this guy rotates 90 degrees, the force on the top wire is up, force on the bottom wire is down. So what happens when it goes this way? When it keeps rotating?
It'll stop.
It slows down. And then it would oscillate back and forth. Is that a useful electric motor?
Yeah, for an electric toothbrush.
Only for toothbrushes, though.
Only for toothbrush.
Only toothbrushes.
But the thing is that you're going to lose some kind of energy, though. You're going to lose energy through the motion, and so it would end up oscillating, and it would end up
Just flip it upside down.
it would end up stopping. It would end up stopping.
You get a heated electric toothbrush.
So there are clever ways, and what I'm doing today is all direct current because we can fix this with alternating current. This is my pool pump. This is essentially a small, tiny like drone motor on steroids. But this uses alternating current, and so it's a little more sophisticated. And so that's what Timothy's kind of getting across with his.
You know, direct current just add an alternator.
What?
Just add an alternator using the direct current.
What? Wait, hold on. I can't do more than one thing at once. Okay. So here.
If you do the thing right, it will work.
Okay, sorry about the blurriness at home. I don't know how to fix that. So if you need to get closer, this is up here. I got a wire. I got a loop of wire, and I just looped it around a bunch of times because you might think. And think about this. If I put a bunch of square loops of wire, each wire that comes down here feels the same magnetic force. So I get more overall force with the more loops of wire I have, right? Each wire that's coming down on this side is going to feel that same force because it's going to carry the same current. And so to get more force on a loop of wire, all I do is add more loops, and I get more force without doing anything else. And so what I've done here, I got 2 paper clips pointing up. I've just looped one of these guys, a bunch of loops of wire, and then had the wires stick out to the side so I can put it between the paper clips that are acting as the post. And I have a magnet right here, right? Those little neodymium magnets are right there. And so when I run some juice through this guy, I get some rotation, right?
It sparks.
And then it just
Balls off.
Yeah, let's try it one more time. Play it again, Sam. Okay, we're having issues. Of course, whenever I need it to work. This is when we have issues. There we go. There we go.
Whoa.
So there's an electric motor.
It's spinning.
That's what electric motors do. That's literally all they do. They just spin. They take electrical energy and they convert it to kinetic energy.
That's probably really good.
Now, how is this working? Because, like we just talked about, after it rotates through just 180 degrees, it should feel force that wants to make it go back.
Is that
Right.
direct current?
What's that?
Is that direct current?
This is direct current. This is direct current. So I had to do something kind of clever.
So he induced the magnetic force with the magnet.
Well, yeah, you need the magnets.
Oh, okay.
Here's another loop of wire. I made a slight modification to this wire. Here's another one that I haven't made the modification to. And you might see an effect, but it's not going to spin because I can't even get it onto the stinking paper clips.
No, that's the modification you made.
No.
It fits.
Oh my gosh, what is wrong with me? There. So you might see an effect. You actually probably won't. Nothing. So what I had to do, this wire has a coating on it. It has a coating on it. And so what I had to do is scrape off that coating in order for the thing to feel the magnetic force, in order for current to go through the loop of wire into the other paper clip, right? I should have done this. I should have taken one and stripped off all of that coating. Because if all that coating gets stripped off, then as it rotates, you know, it's going to feel that force that's going to want to make it rotate back to where it started. What I do, though, is I only scrape off half of it. I only scrape off the coating on half of the wire on each side. So that when the connection is made, it causes the force. But then when it's just about to get to 180 degrees, it encounters the part of the wire that is coated, and so it shuts off the current. And so the kinetic energy of the loop carries it through the next 180 degrees to where it reestablishes the current, and then it continues to rotate. So every 180 degrees, it literally shuts off the current, and then the kinetic energy of the loop carries it through. And then after it goes through another 180 degrees, the current is then reestablished. So if you look on this wire up close, you see half of each of these posts here is green, and the other half is metallic.
Is that why you have the light bulbs there to demonstrate that?
Oh, no, that's for something else.
Is that why it's sparking?
Yeah, that's why it's sparking. Every spark that you see is the current getting reestablished. Like 20 volts. Yeah, so each spark there is the current getting
So the
reestablished.
faster it goes, the more sparks you would get.
Yeah,
So the more fire.
more fire. More fire, more better. And if it stops and you run current through it, then it's a short circuit. Because all the energy is being converted to heat, right? And that's why this started smoking yesterday when I was playing with it in one of my other classes.
Smoking's bad.
And then, but if it's rotating, then a lot of that energy goes to rotational kinetic energy. And so you don't have a short circuit anymore because it's not all being converted straight to heat. Okay? Now that is the simplest way to get a motor, is just to design it so that every 180 degrees it shuts off. That's not the most efficient though. That's not the most efficient way of designing an electric motor. And this isn't the most efficient way either, but it is getting more efficient. And so this is called a St. Louis motor.
It's attached to a permanent magnitude motor.
What's that?
Attached to a permanent magnitude motor.
Well, all motors have permanent magnets.
Right, but like rotate the magnetic field also.
Oh, you might be onto something there. So this is a St. Louis motor. It's a motor that is not useful because you really can't do anything with it, but it's very good at visually getting a visual for what's going on, for understanding how the motor works. So if you notice here, I'm going to have my electrodes hooked up. And you can see this on the video. Yeah. So the electrodes are hooked up to this, and then the electricity comes down into these pieces of metal here that are called brushes. Okay. They do have brushless motors. We're not going to really talk about brushless motors in this class, but there are brushless motors. And so those brushes make the electrical contact here, and then they force current through these coils of wire down here. Notice that within those coils of wire, there's actually a piece of iron that gets magnetized as the electricity goes through the coils. And so that there's a lot of different configurations you can have. Anytime you have a current through a wire, in the presence of a magnetic field, you have the potential for a magnetic force. You can magnify those by having that current generate its own magnetic field, because currents generate magnetic fields. You put a piece of iron within that magnetic field, it aligns the domains within the iron and increases the magnetic field strength. And so you get an even stronger electric force or stronger magnetic force, and we can get that motor to do more work, to spin faster. So that's what this one does. The permanent magnets are on the side. But again, this is direct current. This is direct current, and sure enough, when it spins, there's a lot more kinetic energy there, right? A lot less voltage. So this is a lot more efficient transfer of electrical energy to rotational energy. But that's direct current. I should experience that same thing that we talked about, where it should rotate through just 180 degrees and then want to rotate back, right? And so it should never turn through one full rotation. And so the ingenious little device here, and this is pre-digital, this is not digital at all, this is just mechanical, purely mechanical. The device, and did you guys see the sparks as it was spinning?
No.
Oh. Well, you weren't looking hard enough. There were definitely sparks. So the way that you can mechanically fix this problem is with something called a commutator. So are you guys allowed? Are you allowed to handle the same thing? Can I pass this around the room?
Yeah, it's self-sanitizing.
I feel like I'm not allowed to. Come up to the front of the room and take a look at this, one at a time. Okay. And notice.
We can just all have to go to the bathroom one at a time.
Notice the thimble-looking thing that the brushes come into contact with. Okay.
Is that what they use in RC cars? Is this motor? Because the RC cars use brush and brushless motors.
I don't know.
Yeah, I don't.
I just know that because I saw RC cars. That's the only reason why.
That's a good question. I should know that, but I don't.
Well, learn about it.
Maybe I will. God.
What do you mean you can't tell us every single thing about an RC car? You're supposed to be a physics teacher.
I'm sorry. My brother used to race those when we were kids.
I think I got
I tried, but I was terrible at it. You see the thimble thing? And the brushes that are coming down? Look at the thimble thing that's in contact with the brushes. Hmm?
It's switching the
Ah, but it's not. Okay. All right. So what you were looking at? Sorry. I'll wait for Alex.
Hi, Alex. Hold on, class. Ah.
So this is like a top-down view. Go to the AP office. So these are the brushes. Imagine these are the brushes. One is connected to positive, one is negative. Those don't switch. Those don't switch at all. This guy is that thimble-looking guy that is connected. Underneath this, you would have the coils of wire, right? You'd have the coils of wire that are kind of oriented like this. And there's the wire coils. Okay. Honestly, they would be oriented the other way. Dang it. This is Alex's fault.
He took too long.
He threw me off. He took too long.
He's overthinking it now.
Okay. So that it's like this way. Let me actually use red. So this is the wire that you saw. It's underneath though. It's underneath. Those are the coils of wire. These guys are in contact with that thimble-looking guy. Okay. And there's contact between these guys are conductors. If you notice that the thimble had 3 sections, 2 outer sections and then 1 inner section. The outer section, metal, right? Conductors. So this brush touches this metal and puts current down into that wire in the coil beneath it.
But once it touches
What's it? And it goes from this coil to this coil and then up and out through this one, right? The current goes in that direction, right? Are you with me? Which causes rotation, okay? I have the magnet here and a magnet here. These are permanent magnets. One's north, one's south. Those don't change. The current coming in here and exiting there doesn't change, right? But the interaction between the magnetic field between these magnets and the current, right? There's 90 degrees between the current here, whether it's up or down, and the magnetic field. So I get a magnetic force on the wire. Not only that, the direction that the current goes is such that the magnetic field generated within the piece of iron and amplified by the iron is of the opposite polarity of the permanent magnet. So not only do I get a torque on the wire, but I also get a magnetic repulsion, right, between the magnetized piece of iron in the coil, a magnetized repulsion from this side and attraction to that side. But again, if there was no fancy shenanigans going on here, this thing would rotate and then it would stop, or it would pass through it and then it would wobble back and forth. What this thing does is that it reverses the direction of the current in the coil automatically, right? When this unit, this thimble and the wires that are attached to it rotate through 180 degrees, this guy then gets in contact with this brush, this guy then gets in contact with this brush. So right here, this side is connected to the negative voltage, this side is connected to the positive voltage, but then as it rotates through 180 degrees, this guy will then be connected to positive, this guy will then be connected to negative. So it literally reverses the direction of the current, reverses the polarity of the magnetic field generated by the piece of iron within the coil wire. Okay? And it does so every 180 degrees. So every time it goes through 180 degree rotation, the current direction switches and it just continues that cycle over and over and over again. But notice how fast it goes. That's fast, right? It's happening very, very quickly. Many, many, many times per second.
I can spin that fast.
Let's see it.
Little do you know, I have a magnetic motor inside my legs.
Little do you know, I am a magnetic motor.
Did I not? Oh. Hey.
Don't forget to turn the camera.
Oh, there we go.
That's right. There we five.
Yeah, I don't think it's say it again.
It doesn't matter because it's broken.
So Alex.
You overthought it again.
Alex, gosh. There's no current going through it.
It's because Alex is there just stopping the current.
That's at Alex AP office.
Go past one to me.
Yeah, go take your exam right then.
Okay, I understand what's going on.
Is the power on?
Yeah.
Try turning it on and turning it off.
Is it GFCI strip?
Now the voltage is up. There we go.
It's sparking.
There we go.
Whoops.
So you're basically proving that it doesn't work.
Ah, there we go. Now it's spinning.
There, now it's spinning.
Well, I mean,
Okay, I think our St. Louis motor has been busted. So
we're having to reinvent basic electric motors right now. Give them a little bit of time.
I blame you. You guys did something too when you're looking at it.
Now,
Okay, anyway.
With this one.
Hopefully you understand what I was getting at there. Sorry about that at home, people at home. So this configuration is called a commutator. It's called a commutator. It involves brushes and that thing right there, and it's just used to reverse the direction of the electric current, so that you get a continual oscillation of the magnetic field, and so it just continues. Did you get what I'm getting at?
Yeah.
So and you can improve on that, right? That's only two. That's only two sides of the commutator there. You can actually improve on that. In this little tiny motor, this is like a drone motor or some kind of motor done to get something small to spin. There's 3 coils of wire, and then 2 permanent magnets. And so now it's going to be a little. I would pass this around, but I'm not allowed to. But there's 2 points of contact, just like there are here. But there's 3 coils of wire. And if you look, for every rotation, you actually get 2 switchings of the direction of the current every 1 rotation, based on the configuration that it has. So the more often you switch the direction, the more efficient your electric motor is going to be. Does that make sense?
Every 1
'Cause
to
it-
3.
Yeah. Well, when you start looking at more complicated motors like the ceiling fan motor, which is actually a brushless motor, but it operates on the same general principles. You got a whole lot of current reversals every second. Every rotation, you get a whole lot. Basic idea, coils of wire on something that can rotate, magnets create, that's what electric motors are, okay? And I like bringing in my pool pump, well, at least this year, because it crapped out about 2 weeks ago and I had to replace it. But if I opened it up, you look in your pool pump, it's just the center post, it spins, right? And that happens because you have a central rotor that's a magnet surrounded by a stator, which contains all the coils of wire, and it's the interaction between those two. And this goes to alternating current. That it's just to spin. Like this thing does the same thing as what a very tiny motor does, or like this St. Louis motor does, or this little tiny motor here. Right? It's just this little post here just rotates. That's it. That's what electric motors do. They rotate. So that's what a pool pump does.
Seems like a pretty good dental tool.
That's what they do. Unless they're yeah.
Alright, hold on.
But your pool pump does the same thing as this. You got a pool, right? You said you had a pool?
Yeah.
So instead of like having a propeller on the post here, you have an impeller, which is, if you've ever been on a jet ski, it's like a jet ski impeller. Most boat motors actually just propel water out. You have the blades that hit the water and force it out this way. Conservation momentum says the momentum of the water this way is the momentum of the boat that way. An impeller is kind of the same, only it's enclosed within a channel to kind of direct the water along that tube, and so it comes out much more streamlined, and so you get the jet ski to move in the opposite direction. Same thing in your pool pump. In your pool pump, it's a little different. It's like a fan blade, but it's encased on both sides. So as it spins, it just gathers the water up and forces it out the other end. But most of the motor is just wire and magnets. That's it. And it's just designed to spin the impeller, which is in the enclosure of the pump itself. That's just the pump motor. So that's what electric motors do. They spin. They take electrical energy and they convert it to rotational kinetic energy. Ceiling fan motors, your blenders that you use in the kitchen, electric motors in anything that spins. Yeah.
What about the blender I use in the garage?
Not that one.
What about the bean blender?
The bean blender, yes. All bean blenders use electric motors. Okay, we didn't get to where I wanted to get today, but we'll talk about that tomorrow. Are you guys going to be here tomorrow?
I'm arriving late.
Okay, I'm going to have you guys watch some Dan Fullerton videos then tomorrow. Because we're going to, they keep taking days away and we're going to fall behind and like hopelessly behind. So I'll send out a remind tomorrow to watch the Dan Fullerton videos tomorrow before you come in on Friday. It's going to be on the BIOS of Art Law. Fun stuff.
After